So I'm going to continue in the tradition of saying nice things about Bruce. But, you know, a lot of what you're going to see here, you know, was only really possible with the development of the tools that allowed us to do the sorts of research that we wanted to do and we were interested in doing. And really, there was nothing like FreeSurfer at the time as it's being developed. And I'm going to give you a little bit of my historic perspective coming to the lab, and provide a little bit of context as to why what Bruce and Anders and the whole FreeSurfer team was doing at the time that made it so unique. So I just want to start. I mean, if we're talking about 20 years, what was going on in 1997? It was a very different time for, there was no Twitter. All of the news was a little bit different than what we have now. Some of the big stories at the time, the death of Princess Diana. There was a very memorable fight between Mike Tyson and Evander Holyfield. Tiger Woods became the youngest person to win the Masters tournament. Michael Jackson had a baby, Prince. Titanic was the big movie at the time. It was the highest grossing film of all time, and for the next several years. And we were all accessing the internet using Netscape and using a dial-up modem at 28.8 kilobits per second. In case you're wondering what the music was like back then, it was a lot more, it was a lot lighter than the music of today. Hanson was pretty big. The Spice Girls dominated in 1997. Sugar Ray with that, really happy alternative rock with Fly, and Third Eye Blind. So this is kind of our musical scene then. But at the MGH NMR Center at the time, there were there was a variety of amazing types of projects that were coming out from the functional imaging work going on there. Whoops, sorry about that. Yep, that's that again. As we heard about in our last celebration, some of the okay, sorry about that. Some of the early work in the center defining some of these retinotopic areas. This had already been going on for some time, as Marty Serino just showed a little while back. But by 1997, this was an art form at the NMR Center, but what was really unique about this work compared to a lot of functional imaging work were these cortical models, were these models that were being used to display, in addition to the functional work that was being performed, but these cortical models that were being used to display the data in a way that nobody else was doing, and in a way that was necessary for any kind of interpretation of the data. As you could see here, mapping these retinotopic visual areas, if you look at this information as blobs in a volume, you have no idea what you're looking at, as has been demonstrated many times over the years. But by having these explicit representations of the cortex, you can get to these maps that are much more scientifically insightful as to the nature of visual processing. In the structural imaging world, things were a little bit different. This is actually a figure that a journal allowed us to publish from my work at that time, where we were basically doing morphometric measurements from the corpus callosum. And to do that, we were manually tracing a single slice of the corpus callosum on this beautiful image that you see here, and basically tracing out the intracranial cavity, tracing out the cerebellum in this mid-sagittal slice so that we had a few measurements to work with. In the course of my graduate work, I moved on to starting to trace out the prefrontal cortex using, again, these sort of low-resolution, two-dimensional scans, both tracing the outer cortical boundaries and the gray matter, white matter boundary on a sort of slice-by-slice basis, allowing us to measure a small part of the brain. And then I got crazy and decided I was going to try to do gyral boundaries, as you can see here, again, going sort of slice-by-slice through the brain, trying to measure, for example, the superior frontal gyrus, middle frontal gyrus, and trying to get structural measurements from these images. This is extremely time-consuming, obviously. It's extremely difficult, and it's extremely it's difficult to get accurately well. So obviously, this paper by Anders Bruce and colleagues in 1999, and of course Dr. Serino, in 1999, was sort of something that I found to be groundbreaking in the descriptions of the ways that they were creating these cortical models. And in particular, I believe this is the last paragraph of the 1999 paper, and it's a long segment, but I want to read it because it was very exciting to me when I saw it. Finally, it has not escaped our attention. Oh, and by the way, that having explicit representations of both the gray, white, and the peel surfaces allow us to compute a variety of morphometric properties of the cortex, such as gray matter volume, thickness, degree of folding. When such measures are combined with automated procedures, morphing individual subjects into a standardized space of surface-based coordinate system, blah, 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 blah. Largely automated nature of these methods described here facilitates the routine use of such analysis techniques in a wide range of applications, including the study of psychiatric and neurodegenerative diseases. This was extremely exciting to me because I was ready to move on to largely automated procedures, and particularly procedures that were going to allow me to quantify information throughout the entire brain. Around the same time, Randy Buckner and his colleagues at Washington University who had been collaborating with Anders for quite some time, were developing a large database of MRI images. I believe the first of its kind publicly available data set for measuring of individuals that were sort of across the age span, as well adult age span, as well as individuals with mild cognitive impairment and Alzheimer's disease. And fortunately, we were able to use these images in sort of some of the early applications of the procedures that Bruce had developed to measure cortical thickness. So this is from one of the initial studies that I worked on with Bruce, basically looking at changes in cortical thickness as a result of aging. So this is a figure that maybe many of you have seen, but it's basically using the cortical surfaces to measure the thickness. And you see the color scale here going from thin cortex in dark colors to thicker cortex in the brighter yellow colors. And these are young adult men and women, a middle-aged adult man and a middle-aged adult woman, an older adult man, an older adult woman. And you can see clearly just visually that the colors change from sort of a brighter yellow to a darker red here. And through the amazing cortical registration procedures, we were able to actually do a point-by-point statistical analysis of the data and get these sorts of statistical maps that you see here. That basically what you see here is the color scale showing regions that were statistically associated with age, and with the brightest yellow colors being the regions that show the strongest associations with age. And what was surprising at the time, and not having the ability to do these sorts of analyses prior to this, there was a very strong focus on sort of a prefrontal-centric view of how the brain ages. This idea that really the prefrontal cortex is selectively vulnerable to aging, and that pretty much a good amount of the rest of the cortex, particularly motor and somatosensory, and motor and visual cortex, would be relatively spared. But obviously, as you see here, there's sort of a widespread set of regions that show this sort of change in cortical thickness with aging, not necessarily limited and not necessarily uniform throughout the prefrontal cortex. And these were the sorts of insights that we were able to have by basically having the ability to do these automated procedures in a large number of subjects and look throughout the entire cerebral cortex. And I have to throw a little shout out to Doug here in the development of the RECON-ALL procedure, which actually made this all, these large data sets possible, because the other, memory I have of kind of coming to the lab was doing a lot of command line operations, which I was somewhat incompetent at doing at the time. So when Doug threw kind of all these commands together into the RECON-ALL procedure that we all use now, it made the possibility of sort of these large sample studies happen. So now that's kind of the then portion. I'm just going to quickly talk about a few things from now. Sort of a secondary feature of brain aging that we're very interested in studying are these white matter lesions that occur throughout the brain. And what you could see here are frequency maps across 3 groups of individuals. These are cognitively healthy older adults, individuals with mild cognitive impairment, and individuals with Alzheimer's disease, basically just showing the frequency of the population that have these white matter lesions in each area throughout the brain. And with the lower frequencies being in the red colors, the higher frequencies being in the yellow colors. So as you could see that we know that there's this periventricular accumulation of these types of lesions that occur with both typical aging, but also have sort of a greater frequency in individuals with Alzheimer's disease. And here you could see basically the difference in sort of the percentage points of the individuals with Alzheimer's disease compared to the controls, so that there's a greater degree of lesion deposition in the Alzheimer's patients compared to controls. What's interesting about this is that these lesions are considered independent from the Alzheimer's pathological processes. So these, the typical model of Alzheimer's disease are the plaque and tangle pathology that basically propagates from medial temporal lobe regions in early stages to parietal regions in later stages, and then finally into the later stages out to frontal parts of the brain. These white matter lesions are thought to be more related, or at least presumed to be related, to vascular health. So the idea is that at least that low blood flow areas are susceptible to hypoperfusion, and that contributes some ischemic tissue damage and results, at least in part, to these lesions. But there's still some limitations in how we quantify these lesions. In particular, there's really not been any good way of localizing where these lesions occur. You see a lot of these maps that basically show these properties in terms of their periventricular or sort of distributed spatial nature, but not really any information about where they occur relative to, for example, pericortical regions. And also, it's been a little bit difficult to quantify them because typically people look at them as sort of a single volume, or the total amount of white matter lesion, when in fact the spatial distribution may be an important parameter. So fortunately, another tool that was developed while in the last several years was this ability to not just parcellate the cortical parts, regions of the brain, but also sort of diffuse that cortical parcellation into the white matter, so we can start to get measurements from the white matter that give us some information about its spatial proximity to cortical regions. And just very recently, Emily Lindemer, a graduate student in the HST program, worked with Bruce and Doug to develop a new way of both measuring the white matter lesions from multispectral MRI data, but also on ways of quantifying the lesion, the degree of lesion deposition spatially. And what you could see here is she basically used these white matter parcellations from derived from the cortical parcellations to create this sort of staging map of where the lesions accumulate with increasing lesion total volume. So basically, this is how the lesions scale throughout the brain with regard to their pericortical locations. And you can see that basically there you have some of these frontal parietal regions that start with the sort of in the early stages, or the people with sort of low total lesion burden, but that the accumulation tends to spread out again with some of these frontal parietal areas. And what she could do with this information was actually create a quantitative staging procedure where she could use this in the same way that people had staged neuropathological data in conditions like Alzheimer's disease to give an individual a score of stage 1, stage 2, stage 3 for their lesion volume. She additionally used it to quantify any differences in that staging in individuals with Alzheimer's disease. And what you're looking at here are basically 2 different maps showing differences in Alzheimer's patients in the way that they scale in terms of their total lesion volume with regional lesion volume. So basically, you're looking at maps where the Alzheimer's patients have an unanticipated increase in the regional lesion burden compared to what would have been expected from their global burden, meaning where the amount of lesion is different than in the controls. And what you could see is that there's this pattern of these lateral temporal regions, this lateral cortical region, medial frontal, and these, as well as these medial temporal regions. Doing the analyses two different ways, but those are the sorts of regions that pop up as sort of the regions that are most different in the Alzheimer's patients compared to the controls with regard to where you would expect the lesions to be. And what's really interesting about this, and again, the sort of thing that we can do by having these tools that allow us to quantify multiple parameters simultaneously, is we can look at where the lesions are, or where the lesions accumulate differentially in the Alzheimer's patients, and we can match it to patterns of other types of changes that we see in Alzheimer's disease, such as cortical thinning. So what you're looking at on the left, again, is this area of lesion burden in Alzheimer's patients. What you're looking at on the right is patterns of cortical thinning in Alzheimer's disease. And what you see that's interesting just qualitatively from looking at these two maps together is that there seems to be some regional overlap between the spatial patterns of these two different classes of change in the brain. Again, as I said earlier, given that we think that the white matter lesions are an independent process that's related to vascular health, there's really no reason why we would think that the Alzheimer's patients would have a differential distribution of these lesions, and there's also no reason why they should show such a strong spatial correspondence with the sorts of classical cortical pathology that we see in Alzheimer's disease. So this is something that we're interested in pursuing further. So I'll just end by saying, we've gone from this to all of these great tools that we can use to measure a variety of properties throughout the brain that we were not able to do prior. I think that the tools are, it's important to note that the tools are not just tools. The tools are ways of looking at scientific phenomena that we couldn't do otherwise, and it's been instrumental in my professional career to have access to these tools and to have access to the group of people that developed them and their receptiveness to the sorts of requests and ideas that we have in working with them. And so I'm just going to end with this slide. This is a mug that was made by Peng Yu, who was an HST student in 2008 and distributed to various people in the FreeSurfer lab, and I was lucky enough to get one, but it says, as you can see, we love FreeSurfer. And also, obviously there are lots of people involved to thank, including Bruce, Doug, and Anders, who I worked closely with initially coming to the NMR Center, Martino Center, but also all of the people that I've collaborated with and worked with throughout the years since. Thanks.